I'm going to start off just by saying a few words on the general concept of blending. What is it? What do we know about it so far for LSST specifically? What's the severity of it? Why do we care about for science? My name is James Buchanan. I'm a postdoc at Lawrence Livermore National Laboratory, and I'm also the co-convener, along with Cyril Dew, of the Blending Working Group and the Dark Energy Science Collaboration. It's a really fun job because I get to look at all the crazy stuff people are doing to tackle blending. It also makes it a really challenging job because I have to keep track of all the crazy stuff people are doing to tackle blending. I hope maybe with at least this introduction, I can give people a common foundation maybe with which to speak and also introduce anyone who's brand new to the subject. So now let me see if I can, So here's a general plan for kind of the speakers. I don't think I actually have all the speakers listed on this plan because we've had a last minute addition. But hopefully we'll have some time for more general discussion at the end. The first few talks are going to highlight work, especially that's been done, published / released in just the past couple of years. Although in Ismail's talk, we will have some shout outs to some ongoing work as well from a lot of people, because there is a lot of work ongoing from people on all sorts of aspects of the problem, and a lot of work that's been published recently on lots of things related to blending. One thing we will not be talking about in this session, but which is entirely relevant to blending, is synthetic source injection, because we had another breakout session on that earlier today. So I hope if you're interested in synthetic source injection, you went to that breakout session, because we're not going to be talking about it here. So just the general subject of blending, remember that it's going to be the rule, not the exception for LSST. Broadly speaking, objects have about a 2/3 chance of being blended with other objects in the full survey depth. So yeah, we're going to be handed these really crowded images filled with things. What do we do about that? Let me talk about what we do now and the pipelines starting from coads. I know Fred might say something about what we do for calyx just a little bit, but I'm going to start from coads here. And what we do to begin with, if you're given a coad, is you need to start by making footprints. Oh, I see. Aha. Thank you very much. Great, that looks better. So we're going to start by making footprints, which means that we convolve our coad with a circular Gaussian approximation of the point spread function in that coad to form a signal-to-noise image. In that signal-to-noise image, we identify pixels that are above a 5 sigma threshold to form what I call proto-footprints. We blob all those pixels together to form initial cores for our footprints, and then we expand those cores outward by taking each of those detected pixels and expanding them with a diamond shape that's 2.4 times the size of the PSF. We merge any of the results together to form our final set of footprints. Now within those, So just to recap what I just said with an illustration, here's a coad from the DC2 simulations in I-band. This is one patch. Here's what happens when you smooth it out to make your signal-to-noise image. And then you detect all the points in that image that are above a 5 sigma threshold, and then you expand those outward to get our final set of footprints. You can see that this thing is just chock full of footprints, and a lot of these footprints are likely to contain more than one thing. So how many things are there exactly in this image? Well, here's where we need to detect peaks. So looking just inside the footprint pixels, we look for peaks, intensity peaks in the signal-to-noise image. Each of these peaks is associated to a distinct object. Then finally, this has all been done in just a single band so far. We do this independently in all 6 bands. And then we need to merge the bands to make our merged footprints and peak collections. Merging footprints across bands is pretty straightforward. You can just take the union of their pixels to get a common merged footprint. Merging the peaks, we start by assigning a priority order to the bands, starting from I bands, presumably, and then going down successively through lower signal-to-noise bands, so starting from I band and R bands and so on and so forth. So we take all the peaks in I band, and now looking at R band, if there's any peaks in R band that are within 1/3 of an arc second of peaks in I band, we say that those are the same peak. If there's any peaks in I band, or if there's any peaks in R band that are more than an arcsecond away from peaks in I bands, we say that those are totally different things, and that we've just detected the second thing in R band for the first time. You'll notice that I've omitted an intermediate range where we just drop peaks entirely. All right. So that's how we get our merged footprints and our merged peak collections. And finally, we have this merged footprints and peaks, and here's the point where we need to decide how to deblend it in the pipelines. All right, so that's the detection step. Then we get to the deblending step. I hope that's clear as it can be. Just to illustrate the way that this works on a couple of galaxies in particular, here's a galaxy taken from an I-band coed in DC2. This is kind of your standard issue galaxy image that we're going to be seeing. And on the left, or sorry, on the right is the signal to noise image for this galaxy. And you can see there's one peak. This is good because there's only one object here. So here we've correctly counted up the number of objects. And this is a pretty well isolated thing because it belongs to its own footprint. So this is about as good as you can possibly do. Here are two objects, two pretty well separated objects, but they are still technically in the same footprint. So these will be deblended, but we're probably going to be pretty successful at deblending these separate things just because they're so well separated. This is another example where we successfully count up the number of peaks. In the signal to noise image, there's two peaks corresponding to the two separate objects. We don't always do so well. Here's an example where we have two objects that are profoundly overlapped. And on the signal to noise image, you only see one peak. This is an example of an unrecognized blend. So blending can change the actual number of objects that you detect with a particular method. But that's not the only problem. Even if we know that there's two objects here, even if we have some means of deducing that there's two objects in this blend, we're probably not going to be able to measure the properties of these two objects separately very reliably. We're going to try, but we're probably not going to be able to disentangle these objects very effectively. We're going to have a lot of uncertainty on that. I've thrown a lot of very specific numbers at you, and I hope by doing that I've raised some reasonable questions in your mind. Is a 5 sigma threshold the best possible threshold to use for footprint detection? Is a 2.4 times the PSF width the best possible expansion kernel to use for detection? Is peak finding the best possible way to detect objects? These have all been kind of tuned before for like HSC, for example, but these would be excellent topics for people to study in the future as we move forward. I've done some of that work myself, just seeing what happens when you tweak these numbers and seeing how that affects your collections of objects that you get at the end of the day. And some of that's been published in the paper I've linked to at the bottom here. And I think I've also concluded that we can do better than peak finding. So I presented one approach, but I think the moral of the story is we can do better than peak finding. So that's one thing to keep in mind, but that's still sort of preliminary. So it's not pipeline ready yet. Yeah.
Your list of arbitrary numbers, there was at 0.3 and 1 arcsecond.
Yes, exactly.
And I don't know if that is also something to be debated.
I think, yeah, those are basically arbitrary numbers as well, and those would be also great things to study. He was talking about the 0.3 arcsecond and the 1 arcsecond thresholds for merging the peak collections in this. Yeah, just every part of this, we're doing the best we can, and we've chosen what we think are good numbers, but they can all be tuned, I think. Yeah, so broadly speaking, okay, I've been talking about blending. What actually is blending? Sort of implicitly, we think of blending as you have a lot of objects out in space, but when you look at them from Earth, they can accidentally overlap with each other along the same line of sight when we see them through our telescopes. And we say that an object is significantly blended with another object if its properties cannot be well measured without some special compensation. We have a lot of measurement algorithms that I guess work great if we think that objects are isolated, but if they fail to work great, then we say something is significantly blended. But people have tried to be a little more precise than what I've just said. So one definition that was used in sort of review perspectives paper in Nature Physics was that objects are blended with other objects if they're in the same detection footprint. Now, using this definition, we get these fantastic plots that I've gleefully stolen from Melchior et al. 2021. And on the plot on the left here, the blue curve represents the fraction of objects at particular brightness that are blended with any other object in the same detection footprint. And this is again taken from DC2, so this is meant to be representative of the blend fractions that we will see in LSST. You can see that on the far right of plot A, around magnitude 26, 28, things have maybe a 30% chance of being blended with another object. But on plot B, on the far right, around magnitude 26, 28, the second brightest object in that blend is also going to have magnitude 26 or 28, which means that those blends are going to be pretty problematic if you want to measure those things. Contrast this with the far left-hand sides of these plots. In the far left of plot A, you basically have 100% of your objects with brightness 16 or 18. About 100% of those are blended with other things just because they're so darn big. And they're going to be blended with a lot of things. That's the black points on the plot on the left. The black points indicate that things that have a magnitude 18 are blended with about 7 other things in the same footprint. But all is not lost. If you care about those bright things, look on the plot on the right. The plot on the right tells you that the second brightest thing in those magnitude 16 footprints only has a magnitude of 23 or 24. So you could actually probably measure the properties of that magnitude 17 galaxy. You could probably measure that 17 galaxy pretty successfully. But you are not going to be able to measure the properties of the 7 dimmer objects that have been overlapped by that magnitude 17 galaxy. So I hope this gives you a sense of where the problem comes from exactly and what it's going to affect specifically. There have been several other definitions of what blending is put forward. I was looking at footprints in a paper that I wrote, so I said that a footprint is truly blended if it contains 2 or more objects that are sufficiently bright. Sanchez et al. 2021 wrote that an object is truly blended with another object if a sufficient amount of its flux overlaps. These are weasel words, sufficient, enough. This illustrates the point that blending is really not an all or nothing decision. Blending is a spectrum of things along several different axes. How close are the objects? What size are they? What relative brightness do they have? If you have 2 ellipses and one ellipse is kind of overlapping with the edge of another one, that's its own unique thing. The some blends have particular effects on science that others don't have. To start to quantify this, we have a variety of blending metrics that have been introduced. I think Fred's going to talk about a few blending metrics, so I'll leave that to him. And as I've already illustrated, blending affects the number of objects that we detect, as well as their measured properties. So to go back to the case of the large bright galaxy, it can prevent faint overlapping galaxies from being detected in the first place. And it can also cause a lot of spurious detections in the outer edges of the bright galaxies. Preventing spurious detections in the outer edges of a bright galaxy, preventing that is the goal of temporary local background oversubtraction in the detection step. So that's just yet another step in the detection that I hope you've internalized completely now. If we get too many peaks in a footprint, like with that, then we get spurious detections that results in shredding, which is where a single object is shredded into multiple components that it shouldn't be. And if we get too few peaks, we get the case of unrecognized blends. There have been several papers written on the topic of unrecognized blends. What are they? How prevalent are they? How could we identify them better? There's been a lot of interesting work on identifying unrecognized blends more successfully. And Irfan is going to tell us about how unrecognized blends affect the science that we do. And just to be very clear, when I say that objects appear to be overlapping out in space, I don't necessarily mean that they would overlap if you see them through a space telescope. A lot of times when we see them through a telescope on the ground, they only appear to overlap because the PSF spreads their light out and causes the edges of that light to overlap. If that happens, it's reasonable to say that the light from those separate objects just adds together to form the image that we see. And this is a very common assumption in both simulations. I think this was done in the DC2 simulations. Light from separate sources just adds together. And it's also a common assumption in deblenders that we can just add up light. All right? But we know that galaxies contain dust, right? And if you have a galaxy with dust sitting in front of another galaxy, you get something like what's illustrated here, where the foreground galaxy is blocking out, otherwise known as occulting, the light from the galaxy behind it. Now, okay, these things are actually pretty difficult to identify in our existing astronomical data sets. We don't have like huge data sets of these things. There have been a few papers written trying to find these things out there. So maybe this explains why we don't have widely used empirical models for occultation and why we haven't seen a lot of community effort to model this for LSST specific blending studies. But I would like to see a lot more work on this because it's something that happens and we're currently not doing a lot with it. There has been some approximate work done, like in the paper that I've highlighted here, but it would be cool to see more. And finally, okay, genuine galaxy mergers do occur sometimes. They actually occur with some regularity. Let's just maybe think in the back of our heads how we want to handle that. I probably talked for too long already. I just want to emphasize that the pipelines right now perform detection and deblending in a very specific way. That specific way will naturally evolve over the 10 years of LSST. But if you really want to compare it to like early LSST science in particular, you should study how the pipelines are working on that right now, I think, as opposed to studying how source extractor works or as opposed to making a Fisher matrix forecast. These are both useful things to make. I just want to clarify that those are both useful comparisons to have, but they are not actually what we're going to be doing. So I'll leave that out there as my general provocation to the community. Here's a couple of papers of recent deblenders that people have come up with in just the last year. People keep coming up with new deblenders. And I have a lot of extra slides if we have time for extra discussion at the end. That's blending in a nutshell. I encourage everyone to get in touch with the Desk Blending Working Group. I'm one of the co-conveners. We also have Cyril Du, and I put a link to the Desk Confluence page for that if you have access to that. So that's all I have to say. Thanks, everyone. And I think we should go to, let's go to Irfan next, who's going to tell us about the impacts of unrecognized blends on the science that we're doing, to basically say why we should care about this.
Okay, bye. Mask. All right, I'm Irfan Nurbakhsh. I'm going to talk about the effect of unrecognized blends on cosmic shear inference in cosmology. I'm going to open my talk by introducing cosmic shear as a probe of cosmology and by introducing the kind of blending I'm interested in this study. Then I'll describe the mock catalog that is used in this study and the procedure of blending emulation in it. Plus, at the end, of course, you'll see some results and takeaways and a summary. Also, I put the link to the paper that we recently published on this page. You can take a look. And if there are any questions and suggestions and feedback, I would be very happy to receive them. So when we observe the sky, there are correlations in observable quantities for us to measure. Of course, galaxies cluster due to gravity, but the other effect of gravity is the distortion in the shapes of the galaxies in the background, the one that you see here in blue, due to the foreground matter, the one you see in white. These correlations, these distortions are called cosmic shear, and cosmic shear is the focus of this study, by which I mean we are going to take advantage of cosmic shear as a probe to estimate cosmological parameters, and to infer cosmology from our data. But we know real data comes with complications. One of these complications is blending. It turns out when we observe the sky using ground-based telescopes, sometimes we see a picture like this, and we think it's just one galaxy that we detect. But when we observe the same area of the sky with a space-based telescope, for example, here is the comparison is between Subaru and HST. you see two or more galaxies instead of one galaxy. And this is going to introduce some biases in our science that we get from our data. And we want to know to what extent these biases are important. A study by Dawson et al. 2016 estimated about 14% of galaxies in the LSST gold sample are going to be unrecognized blending. And this is the kind of blending I'm interested in. The ones that the observer on the ground does not have any idea, doesn't know that the object that is detected is one galaxy or more. So they think it's just one galaxy. They have no idea about the overlapping galaxies in reality. So to understand what blending does to cosmology, we need to know the truth. We need to know the ground truth as a reference in order to have two sets of cosmological inference and see if blending does anything meaningful to the final conclusions that we get from our data set. So here we chose a buzzword M-body simulation as a simulation for this work. So of course, this simulation doesn't have all of the information we need. For example, galaxy blending is not included in the simulation. We are going to make this simulation LSST-like and then emulate blending in it. So this simulation is about a quarter of the sky, and it has two realizations. So overall, after all of the costs that we have, we're going to get 500 million galaxies to study weak lensing. And that's a good number to start with. So one way of emulating blending and basically identifying galaxy blends in our sample is to generate images for the whole sky. Let's say we have this sky, we just generate images, and we know the truth. We can do a match between the truth catalog and the observed catalog and see which galaxies made a blend, an unrecognized blend, and then we flag them. We can eventually have two cosmological inferences and then see if they're different. But this is very computationally intensive and very time consuming. A better way of doing it is to actually emulate blending, by which I mean you can just go for the areas that are very dense on the sky instead of making images for the whole area. And then for those areas, you can generate images. You can inspect those areas. We don't assume that these galaxies that are closer than some separation angle threshold are automatically unrecognized blends. No, we don't make that assumption. We just take those areas, which is a smaller area of the sky, and then we inspect them. And these are our candidates. And we figure out whether how many of the galaxies in those dense regions are actually unrecognized blend. And then we proceed to the next step in our study. So here's just an example. On the left, you see some galaxies from those crowded regions, dense regions, that are within 4 arcseconds in separation in the sky. And they make these groups, these blend candidates. We make images for these areas. You can see it on the right. And it's going to look like this. So this is created by Galsim, and the detection is done by source extractor through SEP. And here you can see galaxies numbered as 1, 2, and 3 in the truth catalog made an unrecognized blends in the observed catalog. And there are, of course, other kinds of blends that are not the focus of this study. You can see number 7, 8, and 9 here are recognized blends, and we are not going to be concerned with them for this talk. So we would just want to focus on unrecognized blends. And of course, when we group these galaxies for the observed quantities, we can add their second moments, come up with a new shape, and then also we can add their fluxes to come up with a new magnitude per band. So for the same picture I showed you here, is created by the pipeline that is designed for this study. This is just an example to show you how it works. Here on the left, you can see a crowded region with sky noise. On the right, without the sky noise. Just to show you how sky noise is going to change things. And you can see two galaxies here. I hope you can see, yeah. Two galaxies here that are blended unrecognizably. and they're going to have a new shape. Together, they're going to have a combined shape and combined magnitude in our final observed catalog. So it turns out, after doing this emulation, about 12% of the galaxies in my sample that was cut to 24th magnitude in the I band are going to be unrecognized blends. So now that we have the sample, one sample without blending, one sample with blending, we want to know how blending can cause biases in cosmology. Is it important? Is it significant or not? One way is to just measure correlation for the whole sample, but a better way, because of the evolution of the structures in the universe, one way of doing it through redshift, one way of doing it is to make some tomographic bins and use redshift tomography before we actually measure cosmic shear signal. And here for this study, I have 4 tomographic bins, 1, 2, 3, 4. You can see it on the right. And the focus it would be on photo Z here. So I don't want to focus on spec Z. And here on the left, you see 2 plots. One on the y-axis, you see photo Z point estimate. And on the x-axis, you see spec Z, spectroscopic redshift. And the left one is for the non-blended. And the right one is for the case when we have galaxy-galaxy blending in our sample. You see the sigma for this so-called ZZ plot has increased a bit, not that much, but the outlier rate more significantly changed, going from the non-blended sample to blended sample. So before we actually estimate our everything, cosmological parameters, and put error bars in our cosmic shear signal, plus we need to have a covariance matrix. For this study, I did that using 2 methods, one using just a jackknife in the internal covariance estimator, and the other method by using a Gaussian covariance, just to have more than one covariance and see if the results are consistent. So this is the cosmic shear 2-point correlation plus, Cauchy plus on the left and Cauchy minus on the right. On the x-axis, you see the angle, the angular separation, and on the y-axis, you see the cosmic shear signal. For the non-blended sample, you see data points in blue, and for the blended sample, they are shown in orange. As you can see, there is a suppression in the cosmic shear signal due to blending here, and what we want to know is how this suppression can be translated to actual biases in cosmological parameters. And this is what I'm going to show you in the next slide. On the left, you see my results using Gaussian covariance, and on the right, using a jackknife covariance for my sample. In both of these plots, in blue, you see the non-blended case, and in red, you see the blended case. And the fiducial value is just shown here by a green star. We don't see that much change in omega matter, but more noticeable. It is more noticeable in sigma 8, and you see some suppression, a decrease in the value of sigma 8, and because of that, overall, you see a suppression in the value for S8, and this is true for both covariances, both the Gaussian and jackknife covariance. The next slide is showing you a summary of all of these cosmological parameter estimations for different samples. So here you can see a lot of cuts. I don't want you to focus on this one. This is from the paper. But the main focus should be on the non-blended photo Z, the second row, and this one, the sixth row. Photo Z and blending together. So this one and this one. Yes, LSST-like survey, but the difference is that my cut is on I-24th. So I don't have the actual LSST goal sample. So the simulation wasn't deep enough to allow me to go deeper in my sample. So you can see the amount of bias in S8 is more than 2 sigma of the posterior. There's 2 sigma a statistical error in measuring S8 using the posterior that we have here. It is shaded in blue here. I think so, but I'm not sure, you know. So just overall, about 12% of the emulated galaxies in my sample, they were unrecognized blends, and this is probably going to get worse for LSST gold sample. And there is a suppression due to blending in cosmic shear signal. Blending dilutes the cosmic shear signal and introduces correlations in our noise in our sample in a way that are unrelated to lensing, so it is expected. And overall, about 0.025, which is more than 2 sigma of noise, decrease in the S8 parameter, and in both tomographies, and using both Gaussian covariance matrices. So I used two things for each of these claims that I have here. So just to make sure that we are not missing anything. And there is a slight additional bias due to photo Z. And surprisingly, maybe blending did not add that much bias in terms of the redshifts, photo Zs, but I would say the effect of blending was more pronounced in shear measurement. So it had more effects in the actual shapes of the galaxies that we have. But we need more testing to say the final word on the LSST 10-year depth. So the depth of the catalog I had was limited, so it didn't allow me to go as deep as LSST gold sample. And thank you. If there are any questions, suggestions?
Yeah, I have a question. Can anyone hear? Can people online hear me through this mic? Hopefully. But if we have a way of identifying the blends where we think we're really uncertain, and just ignore those entirely and remove those from our analysis, would we do better in our S8 measurement?
You mean by getting rid of them?
Yeah.
I don't have any plot that shows how much of an effect it is, but I would say my first guess is yes, but I don't have anything to rely on in terms of actual evidence, you know.
All right, thanks.
Yeah. Download yours from here.
There was a question from Maroon on Slack. Do you want me to repeat it or?
Yes, please. Sorry, you probably couldn't hear anyone, but yes, please, if you could repeat that, that would be fantastic.
Sure. So Arun.
Yeah, go ahead, Dan. You can repeat that.
No, better if you do it.
Okay, Irfan, you mentioned that blending was affecting shear more than photo Z, but you probably used HSM regaussation. I don't remember which shape measurement method you used, but even with methods like meta-calibration, do you think blending would affect shear more than photo Zs?
Yeah, maybe I should rephrase it in a way that the effect of blending in cosmology is more through the changes in shear than the changes in photo Z. Maybe I should say it this way. It's a more correct way of saying it. So, because I'm not quantifying how it affected the shear, but the cosmic shear signal that we observe after blending is introduced is affected. But we also saw that photo Z is not that affected, so we think the effect of blending on cosmology is more through the shear than the photo Z itself, at least in this study with this depth.
All right. Can I interpret that as even if you have an ideal shear measurement method like that will incur biases.
So yeah, I think maybe it suggests that the way to tackle this problem, this bias that we get due to blending, is better to put our efforts into measuring shapes more accurately than, or at least identifying those blends and getting rid of them more accurately than being concerned about photo Z, at least for this sample that I had. Because my
Thanks,
photo
Irfan.
Z algorithm seemed to be very, very robust against the biases due to blending.
Thanks, Irfan.
Welcome.
Get it, all right, thanks. Okay, so yeah, so now I'm going to be talking about how we're actually deblending things that we do know are there, the deblends that we do have. And so the first thing I'm going to do is I'm going to apologize. So I was one of the early preview people for DALL-E, and so you're going to see a lot of gratuitous use of DALL-E images in this, just because I could, and I'm trying to, there'll be some talk to try and motivate those, but really it was just for fun. Okay, so code of conduct. I think we've gotten that by now. Okay, so right, the general problem, right? James gave a great, probably one of the best introductions I've seen in the problem. So I think that was really good. So I'll just kind of simplify by saying this is a look at a hypersupreme cam image. This is an ultra deep image, so this is going to be a little bit deeper than what you'll see in the 10-year LSST images. But it still gives you a decent idea of what we're going to see, right? Where we're going to see like these large galaxies that are blended with just dozens of objects at times. You're going to see things with different colors mixed together, and blending happening at all different scales, right? And as astronomers, we're not particle physicists, right? We can't just go into a lab and just kind of pick these things out and make measurements on them. We're given what we're given, and we have to try and figure out some way to separate these objects through code. Okay, so how worried should we be about this, right? I think hopefully Irfan, scared you at least a little bit. He scares me a lot. And so if you just kind of look at this at face value, you would almost say we should be like entirely scared. Because so the plots on the right, this is from the HSC wide data, which is a few years of the LSST wide, fast, deep fields. And on the left, this is the ultra deep, which is again a little bit deeper than what LSST is ever going to get to. But I mean, you can see that again, right? Like in the ultra deep, 77% of objects are blended, right? In the other fields, you have as many as like 65% of objects are being blended. And so if you just say, okay, there's a lot of blending going on, that sounds really scary. But hopefully, as I go through this, I'll show that there's some parts of this that are very scary. But hopefully, we'll be able to handle enough of it that it shouldn't be as bad for the things that we actually recognize as blends. Okay, so this is what we're currently doing in the science pipelines. Now, this is subject to change. If anyone out there, as James pointed out, there's a number of new things that are coming out all the time, right? And if someone has something that's better than what we're using, and we can start running tests and show that it works at scale, we'll certainly move to whatever's best, right? This is just what we've been developing in-house over the last few years. Okay, so the first thing is just the single band deblender, right? And so this is what's running on the single visits. So it's just running on a single coed. Actually, no, I'm sorry, not on the coed. This is only running on the single visits, not the coeds. And so this is based on the algorithm that was used in the Sloan deblender. And so basically what it does is it will look at a position of one of the peaks, as James mentioned, that they find, and then it'll look at pixels on opposite sides of that, right? So if you imagine putting the origin at the peak, and then you look at each pixel for x, y, and then minus x, minus y, it takes the minimum of those two pixels and makes a template. And so if you look in this blend here in the bottom left, what you'll see is, for example, this is the symmetric template you would get from this source. So it's essentially something that looks fairly close to what the source looks like. We see for source 2, the peak wasn't actually, this was actually probably two objects. This is probably one of these undetected blends. And you can see that in the symmetric template because there seems to be a peak on both sides of where the actual peak in the catalog was detected. The worst case is if you have something like this source 3, right, where you have very bright objects on opposing sides of it, right? And so now when you build your symmetric template, you're getting some flux from the source up here, you're getting some from the source on the bottom, and so you get something that looks like this. And so most of the flux that the Sloan Deblender is going to have for this object is not actually part of this object, right? And it's more catastrophic than you think, because what it actually does then is after it's made these templates, right? This is just kind of an idea of what we think an object might look like, and is a fairly good estimate for it in a lot of cases. But what happens is then we take these templates, we create we combine them all, and for each pixel we decide what fraction of each source flux from that pixel should be redistributed in it. Right, so it redistributes. It's a flux conserving algorithm. So it's going to redistribute all of the flux from the image based on the weighting fractions from these templates. And so what happens is because this source has stolen flux from both of the other sources, once we go and redistribute it, right, now you look at this one source that we did a pretty good job with its template, but now we're missing a ton of flux from it that the other object stole. Right, so just deblending one object poorly is going to ruin the entire blend, and that's a problem. And that's why we knew we had to move to something better for the co-added images that are going to be deeper. So myself and Peter Melchior, who was then a postdoc and who's now a faculty member at Princeton University, developed a package called Scarlet. And the main the idea that we had is we should do two things. For one, we should take into account color information. So we should be deblending across bands. And the second thing we should do is, instead of just taking these templates and using this really simple template, is we should iterate on them, right? We should try and make the most optimal model that we can. And so that's effectively what we do. So for example, we'll take this source here, right? And we'll model it as a source with two components. We'll say, for example, a bulge and a disk component. And we'll initialize them very similar to the way that, that the Sloan Deblender template looked like. And so what you'll do is you'll have a morphology that is just monochromatic. And then we also have an SED associated with that component. Okay, and so when you combine the morphology and the SED, then you get this color for the component. You do the same for the other component. You combine them and you get a source. You put all the sources together and you get a model. Now notice that this model doesn't really look like our data because we're creating this model in a partially deconvolved frame, right? And the reason you want to do that is because you want to be able to take advantage of the best seeing that you have. Right, you don't want to. We could just try to, make all the PSFs the same, but then we're increasing the blending problem, right? We want to take advantage of having less blending in certain bands, and so what we do is we actually use a Gaussian that's just barely Nyquist sampled, and so that's the frame that our model exists in, and then we'll convolve that into the seeing in each band, and that's what we compare with the data, and then you can see here this would be the residual of that object. It may be a little difficult to see on the projector, but it's still not perfect, right? What you can see is these residuals actually have meaning, right? You see this little blurb over here we didn't get, but that's because in the data, there's actually a source here that wasn't detected, right? The same thing over here, you see kind of this fuzzy area, and again, that's because there's probably either multiple sources right here, or this is a galaxy that has some sort of AGN or something that's more complicated. And so the basic algorithm is pretty much what I just described, except, essentially we use a method that Peter helped develop called AdaProx, which is just a way of putting constraints on our models so that they're updated in each iteration. And so we'll do this somewhere between 20 and iterations usually for each blend. And so then you start to get much better models, okay? But we also don't take these models as the actual truth. What we're currently doing is we're still using these as templates. So then we go back and we redistribute the flux. So again, this is still flux conserving, just like the previous one. It's just that our models should be much better. But you can see some interesting things. So first we'll look at this source here, where our model looks pretty good, right? Our model is, if we look at the residual, right, it's almost spot on except for this source that we didn't detect. It would almost be better in this case if we just use the model, because once we redistribute the flux, now all of a sudden we're adding a little bit of flux from this faint source. But as James showed in his plot, right, this source is much fainter than the actual object, so it might not have as big of an effect. On the other source, this is a case where the model wasn't as good, right, because we had an undetected source or an AGN or something else there. And so we do have, you can see some of these colors in the residuals, which it may be, again, a little hard to see on the monitor, but you see some blue areas over here, you see some orange areas up here. Whereas now once we redistribute the flux and reapportion it, the redistributed model is actually better. And so right now we don't really have a way to tell you which one's going to be better and which one isn't. And so this is, yeah, Michael.
Is there any requirement on monotonicity? Do they have to come down, or can they go back? Can a model go back up again?
Oh yes, thanks. I didn't mention that. Yes, that is one of the constraints that we've added in Scarlet, is we want things to be monotonic. The ensance is essentially, even if you have like a big complicated spiral galaxy, you can decompose it into a bunch of components where each component is like monotonically decreasing from a center. Yeah, thank you. And so just to show real quick, that one that was modeled poorly with a single band bender because it was stealing flux from both sides, now it's modeled much better, right? We've essentially only have the flux from the central object, and it's actually the monoticity that allows us to do that. Because if you try and implement monotonicity on just without optimizing it, you just get all these weird like fractal like spikes and snowflake spikes and everything, and it messes things up even more. But when you iterate on that, then that mostly you can suppress some of that noise. Okay, so in the past year, most of our work has been going from kind of Scarlet, which was really designed not just for ground-based images, but also for like joint reprocessing. So you're deblending ground and space images together. Maybe you have a spectrograph in there, and deblending all these at the same time. Well, that's not what we were really going to have in LSST, right? In Rubin data, we're essentially going to have, it's going to be like a hyperspectral image, right? Where you just have this data cube, everything's on the same pixel grid, everything's aligned to the same WCS. And so we don't need all the machinery that's needed to do those transformations across bands and across instruments. And so you can kind of think of Scarlet as like, if you have a lot of instruments, right, you need this big bulky guy that can carry all this stuff. But if you just have, a single instrument and all of your data's been reprojected to the same frame, you can get away with like this much skinnier person that doesn't need to carry as much. So Scarlet Light is algorithmically identical to Scarlet. Okay, so just to kind of help highlight that, this is the Scarlet model for the blend that we just saw. This is the Scarlet Light model. This is the Scarlet residual. This is the Scarlet Light residual. Right? They're basically the same up to numerical, up to numerical precision. The only difference is essentially in Scarlet, we're calculating the gradients analytically. We're not using another package to do automatic differentiation. And so that saves us a lot in terms of runtime and memory use. And we've also significantly reduced the complexity of the code to make it much easier for other developers other than myself in DM to understand what's going on, and also to decrease some of those transformations that were basically just kind of getting passed through. We can just throw out entire sections of that. And this was really necessary because Scarlet was one of the main bottlenecks for runtime and memory usage in the science pipelines before we implemented it. And so removing autograd and making these changes has given us a significant improvement in performance. And so what you'll see is so there's two different things. So the first thing is these improvements in memory. You can see that there's we save about 2 orders of magnitude less memory by running Scarlet Light. Again, getting identical results. And then in terms of runtime, we get almost an order of magnitude. It's running faster now. I think that it was a good use of our time to do this, because we went from not being sure if we'd have enough compute power to do deblending with Scarlet to now knowing that we have more than enough time and resources. Just to give a kind of a quick look. So this is what the Scarlet model hierarchy looks like. And so like over here, you see that we have a certain branch, and these are all the models to calculate the spectrum and the SED. We have like another set of classes and models to be able to calculate the morphology, others to do the PSF, several different types of sources that are all derived from like a single model class. And this is really needed if you're doing something really complicated, like what Peter and what some of the people doing like strong lensing deblending are doing. This is Scarlet Light, right? We have a blend. It has a bunch of sources and observation. It has one type of source that's made of a bunch of components. The components can be whatever you want them to be. We currently only use a single component that has an SED and morphology in a center, right? So this is much easier for other people to follow and to understand, what we're doing now. As of weekly 26, so unfortunately this came just after the DP 0.2 freeze, but now we are saving the Scarlet models as outputs. So if you load a catalog, you can load the catalog, but you can also just load the Scarlet blend models now. And so you can operate on those. And so that both gives you the advantage of being able to have the actual, like you can have each component's model now, not just the source model, but the individual component models and the entire blend can be recreated. And it's also ended up saving us about an order of magnitude in disk space. And that's because, you can, Scarlet in a way is almost like kind of two things. It's like a decompression algorithm and a deconvolution algorithm. And so essentially we're kind of doing both of those. And you can see that when we store it, we can take advantage of that. I'm not going to go through this in detail. I mostly put this on the slide so that if you want to go look at these later, because I do have some docs that are coming that are going to explain all this. It's actually in peer review right now and has been reviewed. I just have to respond. So that's completely on me. But I wanted to put these in the slide so that if you want to go look at these later, you can just kind of copy and paste and run this in DP 0.2. Well, I'm sorry. If you run the newer pipelines, not 0.2. The last piece that I want to touch on are metrics. And so we're trying to help you identify cases where we know Scarlet's going to do poorly, right? And so some of the metrics I've been looking at have been, for example, looking at like what is the total overlap of footprints this has, right? And so if you look at these blends, essentially all of the sources marked in red, these are sources that overlap above the noise with their neighbors. Everything else is below the noise level. And so, I would say like if you're doing something where you're worried about blending, you could just, for example, just not do all the ones that are overlapping above the noise. Or even better yet, I think a better measurement is what is the fraction of flux from other objects that overlap this with that. So if for example, if I take object 1 and I look at what its flux is, and then I look at the flux from all of the objects that overlap its footprint, right? Because we may not have been to blending as well as we had hoped we had, right? So we want to just look at all the flux from everything. What fraction of that? And if you look at this, we see that these red sources are the only ones that overlap with more than 5% of their flux. Everything has less than 5% of its flux overlapping in the Scarlet model frame, right? And so the key is that we've made these measurements in the deconvolved frame where there isn't as much blending, thinking that the model is essentially telling us that, yes, these in the ground-based images, we might see a lot more blending. We might see like 65% of these sources blended. But if we look in actually the deconvolved frame, which is what the deblender sees, there's only maybe 14% of sources that are blended at that level. And so maybe this isn't quite as scary as we think it is. Now, these are preliminary results, right? And so we're going to have to vet this more. And so anybody else that wants to look at this, I'd be happy to, kind of help walk you through what I did and see other people's ideas. But I think this is really encouraging that maybe blending isn't quite as scary if we know the blends are there. Again, like what Irfan said, like if we don't know what they're there, that's going to be another issue entirely. So what are some things we have coming up? We want to test subtracting models. So one thing we didn't go into is how measurement's done, right? That's a whole nother session. But so we basically have a different way of doing measurements. We want to test fitting maybe only the higher signal to noise portions of the blend, and then for the outskirts, maybe using something like Gaussian mixtures or something else for that to collect, kind of complete all of the flux out in the tails where it should be smoother. We're actually going to make Scarlet its own standalone package. So that way there's going to be much more of a separation between Scarlet and Scarlet Light. And then the other thing is improving initialization around bright objects and crowded fields. And just to give you a quick peek at that, it's because like if this is a crowded field, currently all of those objects, if we initialize them, would be the size of the entire blend. And that's just because of the initialization algorithm we're using. And so there's some significant improvements we'll be making in that. So if you have something like images like these that you're working with and you're like, I can't run Scarlet or Scarlet Light because it's too memory intensive, that is something that we're working on. And hopefully we'll be able to get that out to you soon. All right, thank you.
Question was actually related to exactly that last point. They certainly, the solar system people, I'm sorry, the Milky Way people have been asking for a long time, how low can we go in terms of galactic latitude, or how crowded can we go? Do you have an answer for that with the current Scarlet?
Oh, that is a great question. I should have prepared for, and did not.
No, I didn't expect you to have a number off the top of your head, but it is something that I think the Milky Way community would love to have an answer to, and if there are ideas about how to go to get higher densities, they'll be eager to hear about that.
Yeah, I will say that there is a separate group working on crowded fields, and so I think it's Colin. Can somebody give me a thumbs up or a thumbs down, maybe? Yes, thumbs up. So Colin Slater is working on that, and so there will be a potentially different algorithm that's working in the galactic plane, and then we'll have to see how far we can push Scarlet. But yeah, I don't have a good number for that.
Hi, this is awesome work. Are you going to benchmark Scarlet Light against, like, say, the best you can do with source extractor, for example, so that you sort of link back to what people are used to?
Yeah, so we did that a little bit in our 2018 paper. We haven't gone back to that as much because I think we, at least for ourselves, I mean, we saw that there was just source extractor is almost not a deblender, right? It's more of a segmentation map, because it's every pixel is being associated with the source. It's not actually being kind of redistributed among things. And so I think we probably did as much work, at least initially, with that as we felt we needed to. Okay. But I think if you and other people are like, no, we want to see a bit more proof, then I think we can put in the time to do that, and we should.
I was offering to help with that
one.
So
yes, we should definitely talk now.
And your follow-up question, you use, subpixel flux fractions is something that Scarlet takes care of, and source extractor sort of fudges a little bit. And the benefit for source extractor always was like, well, at least it goes faster. And it sounds like Scarlet Light sort of got rid of that problem as well.
Yeah, it's probably slower, but we're getting closer.
Is it like I have to blink twice slower, or is it I can make a cup of coffee slower?
I honestly don't know. I haven't compared them, so that would be a good comparison.
Well, that was what I was thinking. So yeah.
Yeah.
Okay. Cool.
Cool.
All right. Yeah.
All right. Thanks, Benny.
So I'm not sure I fully understood. So of course we have over 800 visits and 6 bands with angle dithering. So is Scarlet Light operating on some sort of coad in each of the bands?
Oh yeah, I'm sorry if I didn't make that clear. Yeah, it's only operating on the coads. Right.
So your PSF, you did have a step where you did not really smoothing, but where you kind of a filter with a Nyquist sample PSF. How does that work, given that visit will have a different PSF? It's especially important, of course, in RNI band.
Right. So what we do is we use the coed PSFs that are generated by PIF, and so we when we initially create the model, it's actually not very good because we've tried a number of different ways to create a deconvolved model, and sometimes we can even get one with lower signal to noise that just doesn't do well with the gradient descent algorithm. And we found the best is just to start out with the actual observed models and then we convolve that again. So like again, the initial step, it's really puffy because we take those models, we convolve them with a difference kernel between the Scarlet PSF and the observed PSF in each band. And then we back propagate the updates to the gradient updates back through those difference kernels, update the Scarlet space, and then do that again. And that's kind of the iterative procedure there. Did that answer your question? Or?
And it's okay to go to
Yeah, it is. And you know, of course, then there's also the talk of doing like cell-based coads, which then like that is an approximation I'm making here, is that the PSF is the same throughout the whole blend, and that is not always true in these coads. And so there is going to be, yeah, absolutely. So there is going to be some level of error just due to that. Yeah. Mm-hmm.
All right. All right. It looks like we do have a talk from Dan Taranu about multi-profit. So I'm going to start sharing that, and I'll control the slides on that. And Dan, if you want to speak.
Sure, I'll try to go a bit quicker because I guess we have another one after this.
All right.
Okay. So what is multi-profit? It is a multi-band parametric galaxy fitting code replacing C-model and mesh model fit. Basically, it's one of the measurement algorithms that runs on co-added images after they've been deblended, now with Scarlet. I'll show some previous results comparing to Scarlet and other algorithms, but on the current status and some future plans. The current status is basically full rewrite, but I'll get to that. Okay. So features compared to what we have now in mesh model fit, it's multi-band, which the mesh model fit is not. It's just single band. You can do a Gaussian mixture Sursic profile, not just exponential and de Vaucouleurs. You can do anything from n from 0.5 to 8. It computes analytic gradients. You have a flexible PSF and source models, has some various options for parameter transforms, and you can do linear flux optimization, which I'll mention in a bit. Main downside is that it's considerably slower, which is why I'm rewriting it, much in the same way Scarlet Light improved on Scarlet. And we don't have a shapelet PSF, but I don't think that's going to be important. So here's an example, a galaxy from HSC fitting in GRI simultaneously, and the top is a Sursic model, and the bottom is a double Sursic, which, as you expect, gives you slightly better residuals. Then on the next slide, a lower signal-to-noise galaxy. Again, C model on the top, Sursic in the middle, and on the bottom, what we've done is we've taken the best fit Sursic model, which actually did a little bit worse than C model in this case. And all of the individual Gaussian components that build up the Sursic, we've just refit their amplitudes linearly. And that's basically a process that's memory limited rather than CPU limited. It's almost instantaneous to do linear least squares, and you see that significantly improves the model. Okay, there's a GitHub link, but I actually don't want you to download the code yet because, as I said, it's being significantly refactored. Anyway, next slide. Okay, a lot of people ask me, now that Scarlet's working pretty well, why do we still need to do galaxy fitting? And part of that is sort of a general question of non-parametric versus parametric modeling. In a practical sense, I'll show you some results that single Sursic models do pretty well, and we hope that multi-component models would do better. And Fred touched on the idea that basically elliptically symmetric models can do better in low signal-to-noise regions. You can basically model the wings of a PSF as far as you want with Gaussian components probably pretty well, and you could do low surface brightness features like stellar halos and intercluster light and that sort of thing reasonably well. Parametric models also can have some advantages. For example, the Sursic index can be useful. It's sort of vaguely correlated with galaxy morphology. That, of course, depends on the parameterization. And more generally, why not? It's always useful to have multiple algorithms And I'll show you some examples of what we learned just by having multiple algorithms. Okay, so here are some tests I did. These are actually fairly old, so some of these results will probably have changed once we redo them with the current pipelines with Scarlet Light and PIF as the PSF model instead of PSFX. But anyway, for what it's worth, these are comparing R-band magnitudes versus the true source magnitudes from the DC2 catalogs that built what is now DP 0.1 and 0.2. And basically what we're looking at here is, as of about a year ago, Scarlet had a fairly large bias in terms of underestimating the fluxes of bright galaxies. The Sursic model multi-profit was doing a bit better and also with slightly smaller scatter. Vaguely interesting thing is actually multi-profit's implementation of C model did a little bit better than Sursic, which I wasn't expecting. And actually the lesson here is if I were to show you these exact same plots doing single band fitting, they would be quite a lot worse. So in fact, most of the improvement we saw was not from switching from C model to Sursic, it's from doing the fits in multiple bands. I'm not going to show you the same plots for colors. That's a little more favorable for the Sursic model. I think it has the lowest scatter out of all these three. In the next slide, these are showing sizes as a function of magnitude. There's a similar code called ngmix that Aaron Sheldon worked on. I'm going to look at those results first. This is an implementation of a similar kind of C model type of bulge disk model. And we had a long-standing problem before we moved to Scarlet as Deblender that we have a lot of faint galaxies with unreasonably large sizes. And ngmix, even using Scarlet as the models it's fitting, because you're fitting the deblended models, it continued to have this problem. And basically what we learned from this is the size prior is very important. I don't think ngmix was doing anything wrong. It's just that in terms of actually fitting models, it's the size prior allowed galaxies to balloon to unreasonable sizes. Now it turns out just switching from the old Sloan style deblender to Scarlet solved this problem, even with using a C model fit. However, actually I think that middle panel of the title is lying. This is actually mesh model fit working in one band. What you see is there's the histogram of sizes at the right. There's a very sharp peak. This is basically where mesh model fits prior on the galaxy sizes. So if you set your prior too tight, you'll get basically all of your faint galaxies piling up there. And over at the left, we have the Sursic model sizes for multi-profit, and they basically look reasonable. Unfortunately, I don't have comparisons to truth because that's a little bit more complicated. The DC2 galaxies are bulge disk models, so we'd have to convert those to a single effective size. But anyway, just giving, reasonable sizes for faint galaxies was a reasonable win. The other thing I'll point out is, ideally, even though we're intending all these things to be used for measurements of galaxies, not stars, but we still hope that they give reasonable values for stars. You can see in multi-profit, there's a large peak in the size distribution at basically 0 or minus 2.5 on log scale. So those are things that are mostly stars that have 0 size, which is what you expect. But we also see there's an unfortunate tail of around 16 to 17th magnitude, where those are actually stars that we're getting finite sizes for. And that points to problems with either deblending or the PSF model. And I think it's actually mainly the PSF model. Okay, next slide. I did a bit of testing, basically fitting galaxies in our HSC catalog and the Cosmos field in the ultra deep survey that we thought were isolated so basically blends with one source. And I compare the sizes of fitting HSC data versus the HST Cosmos images. And they agreed reasonably well. There were a lot of outliers. Most of those outliers were basically galaxies that were intrinsically very small. But there are also some other ones that appear to have magnitudes also that disagreed wildly. And if you go to the next slide, I guess I'll get on a bit of a soapbox and say Cosmos is sort of our best source of observed truth in the sense that we have very high resolution HST images, which should help a lot with deblending. So just looking at some of those galaxies that went wrong, we can see at the top, there are clearly unrecognized blends where we thought in HSC there was only one source, even though in some of them there's clearly two, even from the ground-based image. You can tell by eye. At the bottom right, even though nominally the HST images aren't quite as deep in a point source magnitude limited sense, background subtraction is also a huge problem. So even though there's clearly one source visible in HST, something went wrong probably with a background subtraction, and the HSC image has too much flux contained, and therefore the galaxy model turns out all wrong. So I think Cosmos is a great resource, but to do these kind of tests to basically work out how well we're doing deblending ground-based images with a higher resolution truth, we need some kind of combined catalog that I don't think exists, even just a source catalog where someone has gone through and done, cross-matching and quality assurance to do detection. To combine ground-based and space-based detection would be very useful for this sort of work. Okay, next slide. Like original Scarlet, multi-profit was too slow, and it's basically I wrote a similarly complex class structure in Python and pre-generated objects and destroyed them unnecessarily. I've been working on fixing that, and basically we're getting an order of magnitude speed up depending on the size of the image and the model we're fitting. I'm hoping to enable multi-scale fitting to try to do, for example, HSC and Cosmos fitting simultaneously, and compare that with how we do with just ground-based imaging alone. There are some other things, but we can save that for later because we're running a bit short on time. Next slide. Yeah, I have a lot of ideas. I think you just ask me about them later, and if you have any burning questions, go ahead. I will point out that priors are basically a big thing we need to work on, not just size priors, but also color priors, which basically I've not really worked on. And conditional priors in the range of 19th mag, where roughly equal probability of a source being a star or a galaxy. So we'll end there and take questions.
All right, thank you. I think we should move right along to Ismail. Are you online?
Yes. Can you hear me?
Yeah, I can hear you. I'm just going to try to load your slides.
Okay. Is it okay if I share them? Make them a bit faster. Or do you...
if we could figure out how to do that in a minute, or I can just continue to share like I'm doing, but.
Okay, yeah, okay. I can do it. Okay. Yeah, thanks for inviting me. So my name is Ismail, a PhD student at the University of Michigan, and I'll be talking about the blending toolkit. And I'll try to make this short because I'm low on time. So sorry if I'm rushing through some things. So the outline is what is blending toolkit? I'll highlight some of the features. I'll say if you want to use it and install it, how do you do that? And then I'll highlight some ongoing work that has been presented in the PCW by some people, and as well as other projects. And then I'll just give a summary. Yeah. So what is blending toolkit? The overall goal is to have a standardized package to evaluate performance metrics for detection, deblending, and measurement algorithms when applied to images of blended objects. So it allows for the creation of data sets of blends and that are reproducible and systematically produced, and that everyone who has a deblending algorithm can compare it, like in the same blends with the same level of noise. That's comparable with LSST-like or other survey simulations. That's the goal. Next slide, please. So I just wanted to highlight, I have a lot of wonderful collaborators that have made Blending Toolkit possible throughout the time that I've been developing, and I just wanted to put everyone here. Next slide, please. So this is just the overall high-level structure of the Blending Toolkit. I won't go through everything in detail, but you basically need a catalog from the sources that you're going to sample to create blends. You need survey information specifying the observer conditions of the posture stems where the blends are drawn. And you need a sampling function that tells us, given the catalog, which are the galaxies that are going to go into each group that is going to form the blends that you see in the posture stems. And then you need a way to generate those blends. We use Gaussian, that's what's in the draw blend generator. Then you need a way of measuring them. So that could be an algorithm like Scarlet, source extractor, or other machine learning based algorithms. And finally, we need metrics. So that's also in BTK. So this is like the pipeline as a whole. And everything that's in red here can be customized and swapped out easily by the user. Next slide, please. Some very quick highlights and features that are in BTK. We can ingest CAT-sim-like catalogs and Cosmos catalogs. And in the future, we'll also be able to ingest Cosmo DC2 catalogs as well. There's two galaxy models. There's a Pulse plus disk model, and there's a Gaussian Cosmos real galaxy model that one of my collaborators, Maxime, implemented. And then for survey information and reference, there's Galsheet, which is a tiny Python library that collects survey references with survey information from LSST, HCC, etc., and has references. So feel free to check it out. I have a link there. And then we also have a measurement interface, and we also have an extensive library of metrics. That's in the last bullet point. Next slide, please. So we very recently released the first official pre-release of the Blending Toolkit version 1.0. And me and the other people on the topical team are focusing on rough edges based on feedback from the community and the blending working group, the Dark Energy Science collaboration. And if you want to try it out and let us, if you have any feedback, that would also be very welcome. Next slide. So now that we're like standardizing some features, adding documentation, we also made it easy to use. It's quick installable. We have a set of tutorial notebooks. We have documentation. And we also have a binary link, which you can just click and you can just run it without installing anything and play with it. And that's how you would pip install it. Next slide, please. I have a bunch of resources for you to get started and more familiar with BTK. What I presented here is just like the peak of the iceberg. There's a lot of features, a lot of documentation, so feel free to explore. And I'll just highlight the last bullet point. We have a Slack channel where me and the rest of the team are, and you can ask us any questions, and we're happy to help. Next slide, please. So now I just want to highlight a few of the ongoing works. There's some presented as posters in the PCW. There's other work that's been done with Blending Toolkit, and it just shows the different ways in which the Blending Toolkit is enabling studies in blending science and systematics. Next slide. So first, there's Andre, who is a recent addition to the topical team. He is an undergrad at Stanford, and he's been working in neural networks using the Blending Toolkit as a data set for neural network galaxy detection in blends. And feel free to reach out to him in Slack if you want to chat more about that. Next slide, please. Then we have Biswajit. He's a PhD student. He's been using the Blending Toolkit as a data set for developing a Bayesian approach to the blending. So it captures the uncertainty that comes from the noise and the blending in like the flux of the galaxies that are in the image. I think he's still in the PCW, and you can also reach out to him in Slack with that handle. Next slide, please. Then Shuang is a postdoc at Stanford. He's been looking at characterizing blending biases in a variety of settings with a focus on clusters and photosea. And you can also reach out to him there, and I believe he's also in the PCW, and he has a poster. Next slide, please. And then there's another set of ongoing projects, which are not directly posters in the PCW, but where Deblending Toolkit is also being used. Next slide. So there's some ongoing effort for combining blending and photo-C in the blending and photo-C working group in Desk. And in particular, in developing metrics for characterizing the effect that blending has on photo-C measurement. And so we started collating this into a GitHub package, which will have metrics that will benefit both working groups. And this is led by Alex Miles, which you can also see his handle in Slack in the top. Next slide, please. Then there's also a PhD student called Pragrut. He's been working on impact of imperfect deblending and photo-C measurements. And he wants to use a blending toolkit for galaxy cluster simulations. So that will be a feature that will be developed and added. Next slide. Then there's work by Nathan Craig, who's an undergrad, and John, who's a professor, on understanding the effect of blending and cosmic shear. So this is related to what Erfan was talking about, that the biggest effect in blending seems to be in the cosmic shear estimation. And so there's ongoing work in using the blending toolkit to characterize the effect of blending on cosmic shear. And they will also develop new features for blending toolkit to do this and metrics. Next slide, please. Then we have a postdoc. His name is Maxim. He's been part of the topical team for a while. And he has implemented the Cosmos real galaxy simulation. So these are more realistic simulations in Gaussian. And he's been using this to study unrecognized blends in the HSC survey. And he's looking to use blending toolkit to develop an ambiguous blend classifier in HSC. Next slide, please. And then this is work by me. So this is a new probabilistic deblender. So it's called BLISS, of aberration light source separator, where we take full astronomical images, and for each image that we detect, we output samples, posterior samples of the source properties, their flux and their shape, etc. And so it basically is probabilistic deblending. You get samples from a catalog, and yeah, it captures uncertainties. And we're looking forward to put this algorithm in BTK and compare with other deblenders. Next slide, please. So just to close, so the blending toolkit can be used to simulate galaxy blends and study the impact of blending on various measurements in a reproducible and systematic way. BTK is quickly becoming a full-fledged Python package and is rapidly converging to a stable version 1.0 release. You can install it and try it today via in the slide that I showed earlier. If you have any interest in blending and interested in simulations of blends or anything related, feel free to join our conversation if you can in the LSST Slack. We'll be happy to have you and hear your ideas or your thoughts of what you're interested in doing with BTK. And finally, there are several ongoing projects characterizing blending biases using BTK. And if you are more interested, you can look at our GitHub that I linked there. Thanks for your attention. I have to take any questions in the minute that I have left.
Thank you, Ismail. Thanks to all our BTKers. Well, as he was saying, I think we got about 2 minutes left, maybe a minute and a half. So any last minute burning questions from the auditorium? Or looks like nothing online in the blue jeans. I will say if you want another perspective on probabilistic catalog building, I've got my poster outside. And also take a look at that. In that case, I think we should give all of our speakers, okay, including myself, one more round of applause. And I hope everyone enjoyed your last breakout session of the PCW. See you all tomorrow.